Imagine standing in front of a massive concrete wall. Behind it, billions of tons of water are waiting. The water stretches for kilometers, and the only thing stopping that enormous body of water from rushing downstream is a giant structure made of concrete and steel, a dam. But here's the incredible question. How can a wall hold back that much water? Water seems harmless. You can hold it in your hands, you can swim through it, you can even pour it into a glass. But put billions of tons of water behind a structure, and suddenly, that same water becomes an enormous engineering challenge. The pressure can be powerful enough to damage concrete, push against the foundation, and force engineers to design every part of the dam with incredible precision. So how do massive dams survive? How do they stop an entire reservoir from breaking through? And what would happen if a dam suddenly failed? The answer begins with something that seems surprisingly simple. Water pressure. The deeper you go underwater, the greater the pressure becomes. At the surface, water pressure is relatively low, but as depth increases, the weight of all the water above you increases. That means the bottom of a deep reservoir experiences far more pressure than the surface, and this creates a major problem for dam engineers. A dam doesn't face equal pressure from top to bottom. The pressure is much greater near the base. Imagine a huge reservoir behind a dam near the surface. The water pushes against the wall relatively gently, but several hundred feet below the surface, an enormous amount of water is pressing against the structure, and that pressure creates a force trying to push the dam downstream. So engineers can't simply build a normal vertical wall and hope it survives. They need a design that can transfer those forces safely into the ground. One of the most famous designs is the gravity dam. It works through an incredibly simple idea: weight. A gravity dam can contain an enormous amount of concrete. The structure is extremely thick near its base and much thinner toward the top. Its massive weight pushes downward, helping resist the horizontal force created by the reservoir. The water pushes the dam forward, while the dam's enormous mass and the strength of its foundation resist that movement. But the dam isn't simply sitting on the ground. The foundation underneath it is extremely important. Engineers have to study the rock beneath the dam. Because the structure is transferring enormous forces into the earth, if the foundation were weak, even an incredibly strong concrete structure could become dangerous. So before construction begins, engineers investigate the geology of the site. They examine the rock, study cracks and weaknesses, analyze groundwater, and determine how the foundation will behave under enormous loads. In many major projects, the foundation is reinforced with deep concrete structures, rock anchors, and other systems designed to connect the dam securely to the surrounding rock. But gravity dams are not the only type. Another fascinating design is the arch dam. Instead of relying mainly on its enormous weight, an arch dam uses its curved shape. Think about a curved bridge. When forces push against the structure, the shape helps transfer those forces toward the sides. An arch dam uses a similar principle. The curved wall faces the reservoir, and the water pushes against it. Instead of allowing all that force to move the wall forward, the arch transfers much of the force into the surrounding rock. That means the dam can sometimes be much thinner compared with a massive gravity dam. But this design requires extremely strong rock on the sides of the valley. The surrounding mountains essentially become part of the structure. And this is one of the most impressive things about dam engineering. The dam itself is only part of the system. The mountain, the foundation, the reservoir. The spillways, the tunnels, the gates, and the power systems all work together because another major challenge is controlling the water. A dam cannot simply hold water forever. Rain falls into the reservoir, rivers continue flowing into it, snow melts in the mountains, and eventually, the water level can rise. If the reservoir becomes too full, the water needs somewhere to go. That's why dams have spillways. A spillway is essentially a controlled path for excess water during normal conditions. Water may remain safely behind the dam, but during heavy rainfall or major floods, the reservoir can rise rapidly. The spillway allows excess water to pass through the dam system without simply overflowing the structure. This is extremely important because uncontrolled water flowing over the top of a dam can cause severe erosion. and once water begins damaging the structure or foundation, the problem can become much more serious. That's why spillways are designed to handle enormous volumes of water. Some look like giant concrete channels, others use massive gates, and some guide water through tunnels deep inside the surrounding rock. When these systems operate, the amount of water moving through them can be incredible. The water can accelerate rapidly, create enormous turbulence, and release huge amounts of energy. That's why spillways are often built with special shapes and surfaces, designed to control the water's speed and direction. The goal isn't simply to let water escape. The goal is to control how that water behaves and prevent it from destroying the structure around it. But dams aren't only built for flood control. Many enormous dams are also power stations, and this is where the stored water becomes something even more useful: hydroelectric power. The reservoir contains enormous potential energy because the water is stored at a higher elevation. When engineers allow that water to move downward through controlled passages, the moving water can spin massive turbines. Those turbines are connected to generators, and the generators produce electricity, so the same water that is being held behind the dam can also be used to power cities, but the process has to be carefully controlled. Water doesn't simply rush through the system at maximum speed. Engineers control the flow, adjust gates, monitor pressure, and manage the turbines, so the system can produce electricity safely inside a hydroelectric power station. The water can travel through enormous pipes called penstocks. These channels direct the water toward the turbines. As the water accelerates, its energy is transferred to the turbine blades. The turbine spins, the generator rotates, and electricity is produced. After passing through the turbine, the water continues downstream, so the dam isn't permanently consuming the water. It is using the energy created by the water's movement and elevation. But storing billions of tons of water also creates another challenge: the reservoir itself. When engineers create a giant reservoir, an enormous area of land can become flooded. Valleys, forests, roads, and sometimes entire communities may be affected. That's why major dam projects can take years of planning. Engineers and scientists have to consider geology, water supply, flood patterns, environmental effects, and the long-term behavior of the reservoir. And once a dam is completed, the work doesn't stop. A giant dam requires constant monitoring. Engineers inspect the concrete, measure movement, monitor water pressure, track seepage, and watch for changes in the surrounding rock. Some dams contain instruments deep inside the structure that can detect tiny changes in movement or pressure, because even a very small change can be important when you're dealing with a structure holding back an enormous reservoir. One of the biggest concerns is seepage. Water can sometimes move through tiny cracks or pathways in the rock and concrete. A small amount of controlled seepage isn't necessarily dangerous. But engineers need to know where the water is going, how much is moving, and whether that amount is changing. If seepage suddenly increases, it can indicate a problem that needs investigation. Another concern is earthquakes. A major dam may be located in a region where the ground can move, so engineers have to consider how the structure will respond to vibrations. The dam must be strong enough and flexible enough to survive the forces created by ground movement. This is another reason the design and foundation matter so much, because the dam isn't only fighting water, it's also connected to the earth itself. And then there's one final question: what happens if a dam actually fails? A catastrophic dam failure can release an enormous volume of water in a very short time. The water can move downstream with tremendous force, flooding areas, destroying infrastructure, and putting lives at risk. That's why dams are designed with multiple safety systems, spillways, emergency gates, drainage systems, monitoring equipment, and carefully engineered foundations all exist to reduce the chances of catastrophic failure. Modern dam engineering is not about building one giant wall and hoping for the best. It's about creating a complete system where every major force has somewhere safe to go. Water pressure is controlled, excess water is released, the foundation carries the load, the structure resists movement, and monitoring systems watch for changes. That's the real secret behind massive dams. They don't defeat the power of water, they work with it. The weight of the dam resists the water. The shape of the structure transfers forces into the foundation. Spillways control excess water, and hydroelectric systems turn the movement of water into useful energy. So the next time you see a gigantic dam, don't just see a concrete wall. Think about what is happening behind it. Billions of tons of water are constantly pushing forward. The pressure increases with depth. The foundation is carrying enormous forces, and every part of the structure has been designed around one simple fact: water is heavy, and when you control enough of it, you are controlling an incredible amount of energy. That's why massive dams are among the most impressive structures humans have ever built. They can hold back entire reservoirs, protect regions from floods, provide drinking and irrigation water, and generate electricity for millions of people. All while standing between a mountain of water and everything downstream. It looks like a simple wall, but behind that wall is some of the most sophisticated engineering on Earth. And perhaps the most fascinating part is that the dam doesn't need to be stronger than the water in every possible way. It only needs to be designed so that the forces created by the water are safely transferred through the structure into the ground and controlled through carefully engineered pathways. That is how a massive concrete wall can hold back billions of tons of water, not by overpowering the ocean, not by stopping physics, but by using physics to control something that seems impossible to control. If you enjoyed this documentary, subscribe to the channel for more fascinating stories about engineering, science, technology, and the incredible machines and structures that make the impossible look completely normal. I'll see you in the next documentary.